the grid that never sleeps. Electricity is one of the few things in modern life that is expected to be instant. You flip a switch, the light turns on. There is no pause, no visible effort, no sense that anything complicated has just occurred. That expectation shapes everything around us. Hospitals assume power will not falter mid-procedure. Data centers assume servers will run continuously. Water systems assume pumps will operate without interruption. Financial markets assume transactions will clear in milliseconds. Electricity is not treated as a service. It is treated as a condition. That confidence is earned through repetition. Hour after hour, day after day, year after year. The grid delivers power so consistently that most people never stop to consider what it takes to make that possible. Because unlike stored resources, electricity must be produced at the exact moment it is used. It cannot wait. It cannot arrive late. It cannot pause while the system catches up. At every moment, generation and consumption must match almost perfectly. Too little power, and voltage collapses. Too much power, and equipment overheats or destabilizes. The margin for error is small. The consequences of imbalance are not. This is why power grids never sleep. They operate continuously, adjusting second by second, responding to millions of independent decisions made by people who never see the system responding to them. A factory powers up machinery. A neighborhood turns on air conditioners. A city wakes. Another goes to sleep. The grid absorbs all of it. Most of the time, it does so invisibly. When it fails, the failure is immediate and unmistakable. Lights go out, signals stop, screens go dark. And suddenly, everything that depended on electricity reveals itself at once. Outages are rarely caused by a single dramatic event. They are usually the result of small disruptions interacting with a system that is already tightly balanced. To understand why blackouts cascade, you first have to understand how the grid came to exist at all. Because electricity did not always move this way, and power was not always something people assumed would simply be there. Part 1. Before the grid existed. Before electric grids, power was local. Not metaphorically local, physically local. If energy was needed, it had to be produced close enough to be used immediately. There was no practical way to move power over distance without losing most of it along the way. Energy did not travel well. It resisted separation from its source. This constraint shaped everything. Early industry formed where power already existed. Mills clustered along rivers because flowing water could turn wheels reliably. Entire towns grew around waterfalls and rapids, not because they were scenic, but because they could do work. When steam power arrived, it changed the source of energy, but not its locality. Factories built their own boilers. Railroads carried fuel, not electricity. Engines powered machines directly through belts, shafts, and gears. If something broke, production stopped. If demand increased, more machinery had to be installed on site. There was no outside system to lean on. Lighting followed the same pattern. Homes and streets were illuminated by oil lamps, gas lines, or flame. Darkness set a firm boundary on daily life. Workdays ended not because tasks were finished, but because visibility was gone. Energy dictated rhythm. Electricity entered this world gradually, and at first it did not disrupt these patterns. Early electrical systems were isolated by necessity. A generator powered a single building, a block, or a small industrial site. Distance introduced resistance. Losses mounted quickly. Beyond a short range, electricity became impractical. Each system stood alone. This isolation created fragility. If a generator failed, everything connected to it went dark. If demand exceeded capacity, lights dimmed or equipment stalled. Maintenance required shutdowns that were felt immediately and completely. Reliability was a local problem with local consequences. At small scale, this was manageable. At larger scale, it was not. As cities grew, so did demand. As factories expanded, so did expectations. Electricity promised flexibility, productivity, and extended hours, but only if it could be made dependable. Dependability required something new: connection. Interconnecting systems allowed power to flow where it was needed most. A generator producing excess capacity could support a nearby system experiencing a surge. Maintenance in one area no longer required total shutdown if another source could compensate. This was not an obvious step. Connection introduced complexity. Different generators had to agree on timing. Voltages had to align. Frequencies had to match. Alternating current made this possible, but only if coordination could be maintained across distance. Electricity stopped being a local utility and started becoming a shared condition. That shift changed how energy was understood. Power was no longer something you owned outright. It was something you participated in. Your demand affected others. Their generation supported you. Your failure could ripple outward. Their stability could carry you through. This interdependence was the birth of the grid. It also marked the end of simple causality. When systems were isolated, problems stayed contained. When systems interconnected, problems could travel. The trade-off was deliberate. Reliability increased dramatically, efficiency improved, costs fell, access expanded. But the system now required constant coordination to remain stable. Electricity was no longer about producing enough. It was about producing exactly enough, everywhere, all the time. That requirement did not relax as the grid grew. It intensified. Part 2. Building synchronization. Once electrical systems began to connect, electricity stopped behaving like a simple resource and started behaving like a system. At first, interconnection was tentative. Small plants linked to neighboring systems cautiously, often for limited hours or specific loads. Engineers understood the benefits of sharing power, but they also understood the risks. When systems tied together, they inherited each other's problems. Early failures reinforced that fear. Generators fell out of step. Voltages drifted. Lights flickered unpredictably. Equipment overheated or shut down without clear cause. These were not dramatic collapses. They were subtle instabilities that made electricity feel unreliable in a new way. Power was no longer simply present or absent. It became inconsistent. The root problem was timing. Alternating current made long-distance transmission practical, but only if every generator agreed on how fast to oscillate. Frequency was not a suggestion. It was a requirement. A generator spinning slightly faster or slower than the rest of the system introduced strain that could not be hidden. When systems disagreed, the disagreement propagated. Motors vibrated, transformers heated, protective devices triggered. At small scale, mismatches could be tolerated briefly. At larger scale, they became destructive. This forced a new kind of discipline. Frequency had to be standardized. Control had to be centralized. Monitoring had to be continuous. Electricity could no longer be managed by individual plant operators acting independently. It required coordination across entire regions. This is where the grid began to look less like infrastructure and more like choreography. Generators hundreds of miles apart had to behave as if they were connected by a single shaft. They had to accelerate and decelerate together. They had to absorb changes without overcorrecting. Synchronization was not automatic. It had to be maintained. Control rooms emerged to manage this task. These rooms did not resemble factory floors or power plants. They were quiet spaces filled with instruments, charts, and displays. Operators watched frequency drift by fractions of a hertz. They monitored line loadings and voltage profiles. They responded to conditions that most people never knew existed. Decisions were small but constant. Increase output slightly, reduce output slightly, shift load, prepare reserves. Nothing dramatic, nothing visible. But without these adjustments, the system would not hold. As grids expanded, operators learned that size could be both a strength and a vulnerability. Larger systems smooth fluctuations. A generator failure in one area could be absorbed by surplus elsewhere. Demand spikes averaged out across geography. Weather variations mattered less when spread across distance. At the same time, scale magnified consequences. A mistake in one control area could affect millions. A failure at the wrong point could overload lines far away. A misjudged response could destabilize an entire region. This tension shaped grid philosophy. Absolute safety margins were abandoned early. They were too expensive. They limited growth. They raised costs for consumers. Instead, grids were designed to operate close to equilibrium. Not recklessly, deliberately. Engineers calculated expected demand, they planned reserves, they accepted that not all capacity would sit idle waiting for rare events. Efficiency mattered. Idle generation represented sunk cost. Overbuilt transmission raised rates. Redundancy had to be justified. The grid became a system optimized for normal conditions with just enough flexibility to absorb predictable variation. This choice was not a flaw, it was a trade-off. Electricity became affordable. Access expanded. Industry grew. Cities spread. The price of that success was sensitivity. A tightly balanced system responds quickly to change. It also reacts strongly when change exceeds expectation. Synchronization made continent-scale grids possible. It also ensured that disturbances would travel as easily as power itself. The grid did not become fragile because engineers ignored risk. It became sensitive because they managed it. They built a system that worked remarkably well, most of the time by trusting coordination over brute force. That trust would be tested repeatedly as demand grew, technology evolved, and the system's complexity deepened. Part 3. How power actually flows. One of the most persistent misunderstandings about electricity is that it behaves like something that can be directed. People imagine power leaving a plant, traveling along a line, and arriving at a specific destination, a home, a factory, a hospital, as if electricity knows where it is supposed to go. It does not. When a generator produces electricity, it adds energy to the grid as a whole. That energy immediately becomes part of a shared electrical field shaped by physics, not planning. From that point on, it flows according to impedance, resistance, and network geometry. Contracts decide who pays for electricity. Physics decides where it flows. This distinction matters because it explains why the grid is difficult to control directly. Operators cannot tell electricity to avoid a particular line. They cannot route it like traffic. They cannot isolate cause and effect cleanly. They can only influence conditions. They adjust generation levels. They manage voltage. They open and close breakers. They rely on protection systems to respond faster than any human ever could. Under stable conditions, this indirect control works extremely well. Demand rises during the day, generation increases, frequency stays steady, demand falls overnight, generation ramps down, the system settles. From the outside, it appears smooth and predictable. Inside the system, constant motion never stops. Every appliance turning on slightly alters local conditions. Every industrial motor introduces reactive power. Every long transmission line behaves like a complex electrical component rather than a simple wire. The grid absorbs millions of these micro-events continuously. Trouble begins when change outpaces response. A large generator trips offline. A transmission line is taken out of service. Weather drives demand far above forecast. None of these events is catastrophic on its own. The problem lies in how the grid reacts. When a component disconnects, its load does not disappear. It moves. Power automatically redistributes along remaining paths, increasing current on other lines. Those lines heat up. Protective relays monitor temperature and current, not context. If thresholds are exceeded, they disconnect. This is not failure, it is design. Equipment is protected first. System stability is secondary. Each protective action is correct locally. Collectively, they can remove capacity faster than the system can compensate. This is the beginning of a cascade. Frequency begins to drift as generation falls behind demand. Voltage drops as reactive power becomes scarce. Motors draw more current to do the same work, increasing stress further. At this point, the grid is not breaking, it is retreating. Components isolate themselves to survive. Islands form, where local generation and load happen to balance. Other areas lose power entirely. From the outside, this looks abrupt. Lights go out with no warning. Entire regions darken in seconds. Inside the control room, the picture is fragmented. Operators see alarms. They see disconnections. They see frequency deviations. They do not see a single cause. They see a system responding to itself. Restoration is slow by necessity. You cannot simply reconnect everything at once. Generators must be synchronized carefully. Load must be added gradually. Each reconnection risks renewed instability. Operators rebuild the grid piece by piece, often starting with power plants. then transmission, then critical loads, and finally residential areas. This process takes hours or days, not because of incompetence, but because precision matters more than speed. Electricity demands agreement. It punishes haste. The grid withdraws cautiously. It returns deliberately. This behavior is often misunderstood as weakness. In reality, it reflects a system designed to protect itself first so it can continue operating afterward. The blackout is not the collapse. It is the pause. Part 4. When balance breaks. For most of its operating life, the grid exists in a narrow band between excess and shortage. It does not aim for comfort, it aims for balance. On a typical day, demand rises and falls in predictable patterns. Morning brings residential use. Midday adds commercial load. Afternoon peaks with cooling or heating demand. Overnight, usage declines. Operators plan for this. Generation schedules are set hours or days in advance. Reserves stand ready to respond. This rhythm is well understood. What challenges the grid are not normal patterns, but convergence. Extreme heat arrives during peak demand hours. A drought reduces hydroelectric output at the same time. A transmission line is already out for maintenance. Fuel delivery is constrained. Forecasts underestimate how quickly conditions will change. None of these factors alone is decisive. Together, they compress the margin the system relies on. Balance becomes fragile, not because the grid lacks capacity, but because flexibility erodes. When reserves are thin, response time matters more than raw power. A generator that can start in 10 minutes is less useful than one that can respond in seconds. A line that could carry extra load under cooler conditions may trip under heat. In these moments, the grid operates in what engineers quietly call edge conditions. There is no buffer to absorb surprises. Everything depends on coordination. Small disturbances that would normally be corrected become destabilizing. A generator trips. A control signal arrives late. A forecast proves optimistic. Protective systems respond instantly. They do what they were built to do. They isolate risk. But isolation shifts burden. Each disconnection increases stress elsewhere. Each adjustment tightens constraints. The grid does not fail loudly. It loses flexibility silently. From the outside, there may be no indication anything is wrong. Lights remain on. Screens stay bright. Air conditioners hum. Inside control rooms, the tone changes. Operators stop planning hours ahead and start reacting minute by minute. Decisions become conservative. Margins are guarded aggressively. Every additional risk is weighed against the possibility of cascading failure. This is the grid under stress. Not broken, not failing, just operating without room to breathe. Human judgment becomes critical at this stage. Automation handles milliseconds. People manage consequences. Operators shed load intentionally to prevent uncontrolled collapse. Rolling blackouts are initiated not because capacity is gone, but because stability is threatened. This choice is often misunderstood. From the public perspective, it looks arbitrary. Why does one neighborhood lose power while another remains lit? From inside the system, it is surgical. Load is reduced where it can be removed safely. Critical infrastructure is preserved. Balance is restored by subtraction rather than addition. These decisions are not taken lightly. They are made to prevent something worse. The grid is designed to survive stress by sacrificing completeness. It prefers partial service over total failure. When balance breaks, the system does not fight to hold everything. It lets go strategically. That restraint is the difference between inconvenience and catastrophe. Part 5. Cascades and blackouts. Large blackouts almost never begin with large events. They begin with ordinary failures. A transmission line contacts vegetation during high wind. A piece of equipment trips after years of reliable service. A protection relay misinterprets a condition it was designed to detect. These are not rare occurrences. They happen constantly across the grid. Most of the time, no one notices. What turns an ordinary failure into a widespread blackout is not the failure itself. It is the system state at the moment the failure occurs. If capacity is plentiful and margins are wide, the grid absorbs the disturbance. Power reroutes. Reserves activate. Stability holds. If margins are thin, the same disturbance can trigger a chain reaction. The grid does not escalate problems deliberately. It responds mechanically. When one component disconnects, its electrical load redistributes automatically. Remaining transmission lines carry more current. Some of them approach limits that were safe minutes earlier. Protection systems monitor those limits constantly. If thresholds are crossed, they act. They disconnect lines to prevent damage. This action removes another pathway for power to flow. Load shifts again. Stress increases elsewhere. This is how cascades form. No single component fails because the entire grid is collapsing. Each fails because it is protecting itself from conditions that now exceed design limits. The sequence unfolds quickly, often faster than operators can intervene. From the public perspective, this speed feels shocking. Entire regions go dark within seconds. No warning, no gradual decline. Inside the system, the process is incremental. Each step follows established rules. Each device responds as intended. The blackout is not chaos. It is order revealing its limits. One of the most unsettling aspects of cascading failures is their unevenness. Some areas lose power immediately. Others remain energized. Critical facilities may stay online while nearby neighborhoods go dark. This is not favoritism. It is topology. Where power flows, where it can reroute, and where it cannot determines outcomes. A substation that loses its last viable supply goes dark regardless of demand. An area with local generation may remain powered even if isolated. Infrastructure designed with redundancy survives longer. This unevenness fuels confusion and frustration. Why here and not there? Why now and not later? The answer is rarely satisfying because it is rooted in physics rather than intention. Restoration is the inverse of failure, and it is deliberately slow. Operators must rebuild the grid in a controlled sequence. Generation must be synchronized. Transmission paths must be energized carefully. Load must be added gradually. Rushing restoration risks restarting the cascade. This is why blackouts can last hours or days, even after the original cause has been addressed. The system must be confident it can hold before it is asked to serve again. Modern grids include many tools designed to limit cascades. Redundancy reduces risk. Automation speeds response. Monitoring improves visibility. But complexity grows alongside capability. Interconnected systems are resilient, but they are also tightly coupled. They react quickly. They share stress. There is no design that eliminates this trade-off. Only designs that manage it differently. Blackouts are not proof that the grid is fragile. They are evidence that it is operating near its limits by choice. That choice has delivered reliable power at enormous scale for generations. It has also ensured that when failure occurs, it is sudden and widespread. This is not a flaw that can be engineered away completely. It is the cost of coordination. Part 6. Why the grid never sleeps. The electric grid is not a structure that can be completed. It has no final state, no moment where the work ends, no point at which it can be left alone. Every second it must respond to the present. Demand changes constantly. Weather shifts. Equipment ages. Human behavior evolves. The grid absorbs all of it in real time. This is why it never truly rests. Control rooms remain staffed at all hours, not because disaster is expected, but because balance is always temporary. Operators monitor conditions that most people never consider. Frequency deviations measured in hundreds of a hertz. Voltage shifts that last seconds. Load patterns that hint at emerging stress. Most of the time, nothing happens. That is the goal. When the grid works well, it fades into the background of daily life. Lights turn on, devices charge. Infrastructure operates smoothly. The absence of interruption becomes normal. That normalcy is deceptive. It hides the effort required to sustain it. The grid depends on continuous stewardship. Maintenance crews replace aging components before failure occurs. Planners model scenarios that may never happen. Engineers debate margins, redundancy, and response time. These choices rarely attract attention. They do not produce visible innovation. They do not promise dramatic transformation. They keep things working. Modern society is layered on this assumption. Water systems rely on electric pumps. Communications depend on powered networks. Healthcare, finance, transportation, and data infrastructure all presume uninterrupted supply. Backup systems exist, but they are bridges, not replacements. The grid is the foundation. When outages occur, they expose how deeply that foundation runs. The disruption feels disproportionate because electricity underlies so much that is otherwise independent. This is not a sign that the system is poorly designed. It is a sign that it is essential. The grid's vulnerabilities are the byproduct of its success. It was built to serve millions, then tens of millions, then hundreds of millions of people. It adapted to new technologies, new demands, and new expectations without ever stopping. That continuity required compromise. Efficiency over excess, coordination over isolation, responsiveness over rigidity. These decisions created a system that can carry enormous load with remarkable reliability. They also ensured that stress would travel quickly when balance breaks. The lesson is not that such systems should be abandoned. It is that they must be tended. Infrastructure that never sleeps requires attention even when it appears calm. Maintenance is not a secondary concern. It is the work. The grid endures because people choose to keep it balanced, because they invest in its upkeep, because they respect its limits. Its quiet persistence makes modern life possible. And like all invisible backbones, its greatest achievement is not that it impresses us when it works. It is that it works at all. Subscribe to The Invisible Backbone. Long-form stories about the systems that quietly hold the modern world together, how they formed, why they matter, and what they are still shaping today.